pretty clear, but be careful not to, give yourself plenty of time, because there's things in there, when you're actually simulating a radar, it's revolving the beam, and you've got a plane flying at it, and I want the time pattern of the return, so you've got to coordinate all that. There's going to be something that you'll have to think through. I say, what else? So in his book, he has a section on filters and on power amplifiers in chapter 10, and we had this little talk about filtering. I guess I should just, out of fairness to you, go through this in terms of the S parameter filter and get the insertion loss and return loss. But I'm going to tell you, a lot of this is going to seem almost too simplistic for you. It really is. So I'm just going to go through this, show you what he's talking about and why. And you know, with basic filters, there's high pass, low pass, and band stop. Those are the types. And we might as well go ahead and just take a look at one of the things he talks about. And I'm just going to tell you that I may do the Butterworth and Chevy filters, but that's really a little advanced. So I'm going to start with a simple filter. Alright, when we talk about filters, I'm going to do it the way he's actually doing it. This is in his book on page 579. So with filters in the S domain, at least, the insertion loss is minus 20 times the log of the magnitude of S to 1. And that's really something that they talk about a lot, the insertion loss, but a lot of times you can have an amplifier, so this will actually be negative, it'll be a gain. Just try to understand it. So what he talks about is taking a look at a simple circuit first, and in his case, he's got a resistor, they put an inductive series with it. So he has this, basically has a system where he has a resistor R, an inductor in series with it, and then another resistor R here. And in his, I want to make sure I don't make this too simple. Yeah. Then he has a source here. And he has a source voltage. And wait a second, I'm sorry. There's something wrong here. I'm going to eliminate this. Just call this R naught. And this is his V in, and this is his V out. So, if you take a look at this, this is almost too simple, but if we wanted to take a look at this and we want a ratio of V out over V in, you all see that this is going to be simple voltage division. So here, this filter would have an impedance, or excuse me, the inductor would have an impedance of J omega L right there. And if you wanted to just write the basic V out over V in, that would be R over, and it would be R, I'll call this R load. R load plus R naught plus J omega L. And that is really, if you're thinking about connecting to transmission lines, this is V2 minus, and that would be over V1 plus. So this would be S21 if we had this in the context of a transmission line. I don't particularly care for this example, but I'm going to do this thing just for everybody's sake. So here, we take a look at this. and we need the magnitude of S21. This is going to be RL over quantity, and it's really going to be the square root of RL plus R naught squared plus, and then it's going to be omega L squared. This is one way to do it. And that would be S21. Now, he calls R naught basically equal to RL in this one. So this R naught, this would be R naught as well, which just means this is going to be R naught here. And this is 2R naught. He does it this way. Something else I'm going to mention here. If this is the case, we can simplify this, and we can just say that's 1 over, and it would be 2 plus J omega L over R. Y'all follow me? I'm dividing top and bottom by R naught, since this is in fact R naught, because he says R naught is RL. You're going to get this. Do y'all follow me in this class? Just because you're dividing by. Okay. Now, if I take this one and I take the magnitude, I have 1 over the square root, and this is going to be 4 plus omega L over R squared. So then, if we take a look at this and get the insertion loss for this one, it's minus 20 times the log of the magnitude of 1 over square root of 4 plus omega L over R naught squared here. And that means it's minus 20 log of 1, which is just 0. And that's minus or plus 20 times the log of this, which is 4 plus omega L over R squared to the 1/2 power. Solve this. There's nothing tricky about this. I'm just I'm inserting S21 to this definition. I'm expanding. So log of A over B is log of A minus log of B. Get this goes away. And when I take a look at this right here, the 1/2 can come out in front. So then I have this equal to 10 times the log of the magnitude of 4 plus omega L over R squared. And you'll plot this and show you that as frequency goes up, there comes one point where it breaks. If we did a Bode plot on this, you can see. So if we plot the insertion loss versus frequency, it really would be the log of that. Then there's going to come a frequency when this will be the same magnitude as this, and that's when it starts breaking upwards. I hope you all understand that. Before this, if you take a look at this, if you let omega be 0, it's 10 log of 4 would be the base level. So you'd be down here, 10 times the log of 4. It's going to stay there until you hit the frequency, and that would be where omega L over R is equal to, or squared, really, it'd be omega L over R equals 2, or omega is equal to 2R over L, and that means F here would be equal to, since this is equal to 2 pi F, I can say that F itself would be equal to R over L pi, and at that point, wherever that is, put it right here, that's when it starts breaking up, and this would be at a rate, because that's squared right there at 20 dB per decade. Now, in his book, he shows you, on the next page, I believe it is, he shows you that plot done. He actually does the actual plot in MATLAB. But I want to make this clear. The real thing with these things is if I give you something like this, and I wanted the insertion loss, the only thing it is you just simply do voltage division, output over input. Take that and just minus 20 times the log of that, and that's it. Now, That happens to be a high pass filter. Do y'all follow me on that? If you take actually, this is the insertion loss. This is not a high pass filter, this is a low pass filter. If you just look at this, you can tell as the frequency goes up, more and more voltages drop there. It's a low pass filter, but that's the insertion loss. And you see the loss goes up and up and up, which means it implies that as this loss gets greater and greater and greater, you're basically losing the signal. You're having more and more loss versus frequency. But he's doing that. If this, just tell me about this one, because I'm going to move on to something in a second. But what would happen if I did this? This would be what? 1 over J omega C is the impedance, right? What would that do? That'd be the opposite effect, right? This is a high pass filter, right? At low frequencies, at DC, there's nothing. Y'all follow me? It would be the exact opposite. So what would the insertion loss be for this one? Let me just do, I want to just talk about this one too, a contrast. Well, for this one, what would it be? So V out over V in, which is really what? V2 minus over V1 plus, if it's in the context of being connected to a transmission line at both ends. Do you follow me on this now? Then what is it going to be? Well, it's still going to be R naught, right? And then it's going to be over 2 R naught, right? Plus 1 over J omega C. Do you agree with that? Right. Now what happens next? Well, depending on how you want to do this, I could go ahead and I could multiply everything by J omega C if I wanted to. You could take that at 1 and divide by R naught. Probably the easiest thing to do would be divide top and bottom by R naught. And if I do that, I get this, right? And then, if I want the magnitude of that, what is it going to be? I'll call this S21. Then the magnitude of S21 would be equal to 1 over the square root of 4, right? Plus 1 over omega RC, R naught C, squared. And then I would take this and stick it, this is the square root of 2 pi. Fold it that way. Take that and stick it into this equation. So we'd be replacing that. And what would come out at the end of the day? I'm just trying to show you this. This would become what? Instead of, it would be 10 log of what? This would become 1 over omega RC, R naught C squared. Then when you plot that, the key would be what? Well, it's coming in from where? This is omega is 0, this is going to be infinite, right? If that's infinite, log of infinity is still infinity. So it's coming in from positive infinity, basically, and it depends on where you break it. But when it actually flattens out is what? When you're at a frequency of 2 would be equal to 1 over omega R naught C, and that means omega naught is equal to, this omega break frequency would be 1 over 2 R naught C, and that's 2 pi F, so it means F itself would be equal to 1 over 4 pi R naught C, and that would be this frequency right here. Now, I'm not going to, and this would be the insertion loss. I'm not going to spend a lot of time, I'm not going to test you on this stuff, but here's one thing I will do. All right, I'm not going to ask you for the insertion loss versus frequency plots for a lot of these. You have to be aware of them. This is something I will do. And I will ask you, it's very basic, but at least you should be able to get it. he goes through some higher order filters. I think he does Chevy Chef and Butterworth. But I'm not worried about that right now. So if I gave you this, and I'm gonna say I have resistor here, and I had a capacitor here, and a resistor here, and this is my input, and I wanted to know, first, for this one, just by looking at it, is it high pass, low pass, band pass, or band stop? Just tell me your reason. It's not hard. Think of what that element does. This is going to be what? 1 over J omega C. So start at the extremes. When omega is 0, it's an open circuit, right? You have a certain output voltage, and it depends on these. If these two resistors are the same, V out is just Vs over 2. Y'all follow me? Now, when all of a sudden this impedance becomes of the order of this, then it starts dropping down, because now, as it gets higher and higher, this becomes the low impedance, and it will drop it down to 0. It's really a low-pass filter, and the cut point would be where, I call it cut point, but where the frequencies, where the output starts falling down, set this equal to that in magnitude. That's the frequency. That's how you find it. So it's flat, and you come down to 20 dB per second. Y'all with me on that? That's a simple. People mess this up. Promise you. All right. Next one I'm going to ask about. Think about this one. Don't say anything yet. Alright. Well, the impedance of this is J omega L. The impedance of this is 1 over J omega C, correct? Now, whenever you see elements like that, an LC in parallel, when it's at resonance, it looks like an open circuit. Y'all hear me on that? Alright. At resonance, this appears as an open circuit. The further off resonance you get, the more it looks like a short. Y'all hear me? So what kind of filter would this? If this has a very small window where it looks like an open circuit, then everywhere else it looks like a short circuit, what kind of a filter would this be? It would basically be what? A band stop. It's going to take a chunk of that frequency domain and just cut it right out. That's all it's doing for the output. What if I had this? Y'all follow me on this. If they're in parallel, LC in parallel, at resonance, it's basically an open circuit. And then further off resonance you get, and we talk about the Q, we can do that later, the more it looks like a short circuit. Y'all hear me? At DC, that inductor looks like a short circuit. At extremely high frequency, the capacitor looks like a short. So now for this. This is J omega L. This is 1 over J omega C. Now, that's a series LC circuit, right? At resonance, it looks like a short. The inductive reactance is equal and opposite the capacitive reactance. Y'all follow me? That's a short circuit at resonance, but the further you get away from resonance, when you're at 0, this looks like an open circuit. As the frequency gets real high, this looks like an open circuit. So this would be a band pass. Y'all follow me? Now you've had these things, I think, in circuits, but I don't remember, did y'all have them in circuits, or did you have them in some? You should have been exposed to them in your laboratory work too, but I don't know if you have or not. All right, now, what about this filter? Just think it through. Go to the limits. When the frequency is 0, the capacitor looks like an open circuit, right? When the frequency is 0, the inductor looks like a short circuit. So we know at DC we get basically V out is equal to Vs over 2, right? Now let frequency go up. What happens? As frequency goes up, more and more voltage drops here, and this is starting to bring down the equivalent impedance of that. So this is going to be a low-pass filter, right? But it's going to have not 20 dB, but 40 dB per decade when you do the math on this one drop, because you have an LNC, all right? You follow me on this, guys? All right, what if I did this? anybody here gone out for an interview recently, for a job interview? Did they give you some kind of they ask you questions, a test like this where they have simple stuff? What was it for, the job?
For rating students from high class micro.
You know, what I'm finding out is more and more these days, they have, you might say, basic questions to make sure that you are what you say you are on your resume. And I'm not kidding about this. And these kind of questions are simple if you know what you're doing, but you'd be surprised how many people kind of stumble around. So here's the next one I'm going to ask about. I'm going to put a capacitor here. All right. And then I'm going to put a capacitor here. Now, what kind of filter is this? Now, just think about it. At DC, what's the output? At DC, it's going to be 0 because this is a blocking capacitor, right? All right. What is it at high frequencies? Well, at high frequencies, this looks like a short, but so does this, right? What it really amounts to is you're going to get voltage division between these two capacitors. Really, you're going to get, whatever the voltage is here, half of it will be here, very high frequencies, right? But that voltage is going to be brought down by the fact that resistance doesn't change, and the net impedance here is going down. So this is going to be really, you take a look at this. It is a type of bandpass filter, but it's not something you're familiar with. Have you done these filters, this kind of stuff? Now, I could put 2 inductors there too, right? That would not pass DC. It would be a short here if that was an inductor, right? At DC. But there would be a band that passes, but this is an odd type of filter because it doesn't have a clear inductance and capacitance. You actually have to write the output versus the input and then plot the thing for some of these filters. Just making you aware of this. I would ask you something probably with LCs in parallel series or a shunt capacitor series inductor type of thing for that. And I'll give you some questions related to that. I'm not going to spend much more time on filters in there because some of this stuff is either overly simplified or really the Chebyshev stuff, and I think he does Butterworth. That's something you're going to get, I think, probably in the senior level design courses. Have you had, when you had analog, did you do any of these filters? Butterworth, Chebyshev, any of that? Just mention them? Okay. All right. So now, this is the thing I wanted to do because of some of the things I've been made aware of. I'm going to go back and do the bounce diagram stuff because this is used for time domain reflectometry all the time. Now, let me give you the usage for what I'm about to show you first. When you have lines, oftentimes they go behind walls. They're not easily accessible anywhere. So what they'll do, if there's a failure in a line somewhere, transmission line, they'll send a pulse through, and it'll hit the spot where there's a discontinuity and reflect back. And just based on the time delay, you can figure out where that fault is in the line. That's one thing. But there's also more to it. So I'm going to go ahead and go through the transient part of transmission lines. This starts on page 87, and we're going back a few chapters. But I want to go through this whole thing and talk to you about how to do really a bounce diagram and do this correctly. That's my goal was today. So normally we assume we have some battery, VS, and we're going to have some resistance, RS here, and then we're going to have a switch that closes at T equals 0, and then we're going to have our transmission line here. And then you're going to have some load here. And the transmission line has a characteristic impedance Z0. Now there's a couple things we're going to do. We're going to get both the current and the voltage at any point in the line. Normally what they'll do is they'll put this at Z equals 0, but it's not necessary. This would be Z equals minus L here. And it has a total length of line L. And they're going to go ahead and get the bounce diagram. Now, how many have had this before? If you had me, you had it. If you didn't have me, you probably didn't have it. But I want to make sure everybody has this thing because this is kind of important in engineering work, and we can talk about this related to some microwave applications, but it has more to do with just basic understanding. That's the reason I'm doing it. So if I'm doing this problem right here, when you're at t equals 0, the circuit actually looks like this. I have plus or minus Vs, and I have some source resistance Rs, and just as that switch closes, it doesn't know how long the line is, so you can replace that entire line with just the characteristic impedance Z0. So this would have impedance of Z0, and then you can get what's called V prime. You can get the voltage right here that's going to occur at the instant that switch closes. This would be at t equals 0. And that value V prime is simply going to be Vs, and it's going to be that times Z0 over Z0 plus Rs. That's your starting point. Now, after that, you need a few other things. I need the reflection coefficient right here. That reflection coefficient is the impedance I'm going into, minus the impedance I came from, which is Z0 over the sum of the two. I need that reflection coefficient at the load, and I need this reflection coefficient this way. The reflection coefficient of the source is the source resistance minus Z0 over Z0 plus Rs. I need that. Now, y'all follow me what I'm doing here? There's also going to be a velocity, a phase velocity on here, which will be c over the square root of epsilon relative of that transmission line. And the reason I need that is because I need to find the delay time from here to here. It's called just the delay time. And that's equal to the length of the line divided by V phase. Now, most of this should make perfect sense, how I got that, right? Distance is velocity, right, times time. I need the time delay for the wave to go from here to here. So after you've got that, we create what's called a bounce diagram. I'm going to do that over here. I'm doing this for everybody's sake. I realized I'm teaching an EMC course. Several people didn't have this before, and this is something that you gotta have, or you really should have in your background if you're going to go out in the field and you're an electrical or computer engineer, because it's used all the time. All right, now when I take a look at this, what do we do a bounce diagram is this. We start, and we're going to graph two things. We're going to graph time on this axis, and this is the position. So this is really, I guess, yeah, this would be at minus L, would be the Z position here. This is 0, or this is the load. And what we do is this. We start at t equals 0 right here, and we draw a line like this, indicating where V prime is propagating. Now, if you think about this, as I go down in time this way, and I look over here, I can see an intersecting point where all of a sudden, at a certain time, the actual V prime waveform will move the distance down the line. It should make sense to you. Once it hits here, there's going to be a reflection coefficient. Basically, this is going to be the reflection coefficient at the load times V prime coming back this way. This time it took to get from here to here will be TD. The time it takes to get back here, this would be 2TD. Still have a spacing of TD there. Then from here, it would go down here and hit this point, and that would be, of course, this is V prime times the reflection coefficient of the load. This would be V prime times the reflection coefficient at the load times the reflection coefficient of the source it would hit, and we keep going like this, and this would be 3TD, and this would be 4TD. So you get the idea, the progression thing, right? Now, if we wanted to get the voltage anywhere on this line, let's just say for now, I want the voltage right in the middle, so I want the voltage here, right in the middle of the line, so V at Z equals minus L over 2, basically halfway down the line. And I'm going to use this bounce diagram to do it. Here's how it's done. You come over here, is gonna be the voltage versus time at the distance z equals minus L over 2, halfway down the line. Well, we know once we close the switch at t equals 0, it takes a certain length of time to get there. It takes exactly TD over 2. You follow me on that? If it takes TD to get all the way down the line, TD over 2. So there's no voltage until I get that point. And that would be TD, whatever it is, over 2. Then it will go up. The way you do this is simply, you start at the point you want. So I wanted z equals minus L over 2. You go straight down, and you can see that at time, it would be TD over 2. This is where V prime happens. So it comes over here, and it goes up to V prime. Y'all follow me? Now, if you keep going on this one, it hits. All right, goes down, hits here, comes back, and if I go straight down, the next intersecting point I hit is going to be the reflection coefficient times V prime. And it will happen exactly once. At t equals 3/2 TD, right? Because it took a full TD to go from there to there. So then at 3/2 TD, right there. Now, and we don't know which way it's going to go. I'm going to go up. Now I'm going to get a value of V prime, the prior value, plus V prime times the reflection coefficient of the load. It's going to stay there until I hit 5/2 TD. So let me just go through what I'm doing. I came down, I started here at 0 until I hit this point. I keep going down, then I have to add this one to the original. Then I go another full TD down here, or 5/2 TD, and now I have to add this part. So then, and let's say it comes down. This is going to be equal to V prime, and I'll just factor out this one. So it's 1 plus reflection coefficient for load, plus reflection coefficient for load times the reflection coefficient for source. And you can see the progression. You're just going to keep on adding terms. Y'all follow me? We'll do a problem like this. Now this is something where this voltage is on there, and it's not a pulse. It's something that's staying there. Pulse would be a little different. There's a comment. Think about this now. As time goes on, and this thing's ricocheting back and forth, it's going to asymptotically approach a constant value. You all get me now? Here's a couple ways to think about this. First of all, this is acting as a transmission line when, usually it's a wavelength, and this is what? Greater than a tenth of a wavelength, right? Well, in the limit, as time goes on, I'm not gonna be too sloppy with this one, the way I'm gonna say it, but as this wave bounces back and forth over time, this starts to look less and less like a transmission line and more like two pieces of wire. And in the limit, as t goes to infinity, that transmission line is just too short. It's a short circuit. You can take this and stick it right here. Y'all follow me? You can eliminate the transmission line altogether and just put the load right next to the source. So what would the voltage have to go to on this line? I'll call it VL at any point as t goes to infinity. This would be as time goes to infinity. It would be what? Simply Vs times RL over RL plus RS. Transmission line has nothing to do with the voltage as t goes to infinity on that line. Does that make sense? Everybody? Now that's just how you know asymptotically where you're going. You're going to find out that after about 3 bounces, it's basically there usually. About right. Now we're going to get the voltage on the line for at the halfway point, and then at the end where the load is, and I'm going to do this based on a problem he has because I want to make sure you see this. Okay. Come out here. And we'll do this. How many haven't had this? How many have not seen this? How many have seen this? Holy mackerel. 1, 2, 3, 4, 5, 6. So about 35% of the class has it. I thought it was some more. Maybe it was. How many had me before? Okay, that explains. All right. Well, anyway, I want to make sure that everybody has this. All right. So. All right, we're going to do, on page 89, he has an example, and he has 4 volts, 25 volt source. This is 75. 75 ohms, the phase velocity is 0.1 C. And the length of this line. It's 6 centimeters long. So the length of this line is 6 centimeters. And we want the voltage right here in the middle of the line. So it's V of time. That's what the first part is. Then we're going to get the voltage at the load. So you got to go ahead and just do this with me. RL for this one. Remember, that's 125 ohms. So this is RL is 1.5 ohms. So the first thing I have to get is this. The reflection coefficient at the load right here is going to be what? 125 minus 75 over 125 plus 75, right? So that's 50, right? Over 200 or 140. Agree with that? Everybody? Down here, what is it? When I come this way, this reflection coefficient source is equal to 25, right, minus 75 over 100, really. So that's going to be equal to minus 1/2. You all agree with that, class? All right. Then when we get our V prime, which is this voltage that goes on the line right there, what is that going to be? Well, the source voltage is 4 volts. I'll put it down. Source voltage times Z naught, right, over Z naught plus R source. So this is equal to 4 times 75 over 75 plus 25. Well, that's 4 times 3/4, 3 volts. Y'all agree with that? I don't mean to bore you with this one, but I have to make sure everybody sees this at least once. So just bear with me. Okay. Now, if we have that as 3 volts, we've got the reflection coefficient. We still need this time. What's the delay time? Class? That's the length of the line, 6 centimeters, right? Over the velocity, which is what? 0.1 times 3 times 10 to the 8. And does it? 8 nanoseconds, is that right? Or not? Oh, never mind, that's 8 nanoseconds. So it's 2 nanoseconds? 2 nanoseconds. So 2 nanoseconds, he wants this thing to go out to 8 nanoseconds. So now over here, right here, I think.
Where did the 0.1 come from in the time delay?
You mean the phase velocity?
Oh, okay, that's the phase.
I'm sorry, this is, he gives it as the velocity on the line.
Okay.
And if you have your books, you can take a look at this. This is like a classic problem. But here's the one we're going for, just so you could get a preview. Instead of this, we're gonna have a pulse. Pulses are much different. We're gonna have something of finite duration. But you gotta start right here to get an understanding of this, to make sure you have an understanding. Okay, now for this one, for the actual bounce diagram, this would be at minus L, this would be 0. If I take a look at this, I'm gonna have this is V prime, this is V prime times the reflection coefficient of the load, V prime reflection coefficient of the load, reflection coefficient of the source, V prime reflection coefficient at the load squared, reflection coefficient of the source, finally, V prime reflection coefficient at the load squared, reflection coefficient of the source squared. And this is positive, so this is 3 volts. This time, right here, is going to be 2 nanoseconds. This time right here is 4 nanoseconds. This time is going to be 6 nanoseconds. And this time is 8 nanoseconds. It wants us to stop there. If this is 3 volts, the reflection coefficient of the load is 1/4, so this is going to be 3/4. Right? And the volt is going this way. This is going to be 3/4 times minus 1/2. So it's minus 3/8 right here. Y'all follow me? I'm just putting in the values, right? If you take 3/4 and multiply it by minus 1/2, it's minus 3/8. I'm not trying to do anything funny here. Finally, this one's the last one we need. So I take minus 3/8 and I multiply it by 1/4. And when I take a look at that, that's minus 3/30 seconds, right? And we can stop there. So now we're going to get this voltage versus time right down this path here. And this is at minus L over 2. And I'll graph it over here. We'll see if we're in agreement with him. I think we are. Then we're going to get the voltage to load. So for that one, let's see. So if TD is 2 nanoseconds, so halfway down would be 1 nanosecond, and it's going to go from 0. This would be V in the middle versus time. 0, and it goes to V prime, which is 3, right? It stays there for what? Right, 1 nanosecond, 3 nanoseconds would be the change, right? And at 3 nanoseconds, I would add on 3/4 to that, so that's going to be 3.75 volts, right? You're going to go up to 3.75 volts. Now we're going to keep going on this one. Next stopping point is what? 5 nanoseconds, and what happens there? Now I have to subtract off 3/8. What does that bring it down to? 3.1. Anyone? Anybody?
3.375.
Sorry. Now what was it again?
3.375.
Right, 3.375. Finally, at 7, let's see. Goes 5 nanoseconds. That's that's 5, so then I have to subtract minus 3/32 after that. I have a point to make now. So can you do that for me? Just take this and subtract off 3/32.
3.28.
3.28. But you can see this thing sort of bouncing around to a steady state value. Now, let's just take a look at where it's going to go way out here. It's going to asymptotically approach a value, and that value is going to be simply Vs times R load over R load plus Rs. For myself, Vs is 4, R load is 125, and that'll be 125 plus 25, 150, right? And what does that come out to? What? 3.32? So this would be 3.33 volts, and you can see we're bouncing around, asymptotically approaching that. Can you all see after about 3 bounces, it's pretty much going to a state where nothing much is going to happen, because now the changes become so slight. But you have to at least have an appreciation for that. Now that's at the center. If we go to the load end and do this, it's a little different. And some of you might remember this, so I want to make sure it covers it. So if we go at the load right there, we're going to use the same bounce diagram. But here is something I'm going to make a point of. So now we're talking about the load voltage. We're right here. Please watch this. If you haven't seen this especially. There's going to be no voltage change at the load until 0, until I hit this point. But at this point, there's 2 things that happen simultaneously. The 3 volts comes in, and the 3/4 volts leaves. So you have to add both of those up. Right? If you think about it, you could get the transmission coefficient, which is 1 plus the reflection coefficient, and multiply that times the actual incoming wave, and you'll get it. But I like to say it's just the simultaneous addition of these 2 things because they're concurrent. They happen at the same time. So if we do the voltage at the load versus time, basically nothing happens until I go 2 nanoseconds, because that's the time delay. And at 2 nanoseconds, it goes up to a value of, what was the sum of these 2? It's 3.75, right? So it goes to 3.75 volts right there, and it's going to stay that way until what? Think about it. That's 6 nanoseconds, correct? Y'all follow? You've got to have, it's the full bounce now. It's got to go back and then back again. So now, that's 2, this would be 4, and this would be 6 nanoseconds, and then at 6 nanoseconds, what happens? Then, to that value, I have to add both minus 3/8 and minus 3/32, because it concurred at that point. There was a voltage before, now you add those 2. What do you get? Well, you're going to add minus 3/8, minus 3/32 to the prior voltage. What is it? Is it 3.28? I'm just curious. 3.28? And it's going to stay there for how long? It's going to, and for 4 more nanoseconds, it stays there. Because you got, so we're really past 8 nanoseconds. That's what it would look like there. Now that's the voltage at the middle and at the end, right? At any other place, you can more or less, let's take a look, go down there if you want it 1/4 of the way, 3/4 of the way, would be the voltage there, but that's how you get this stuff. And by the way, at the source end, you'll notice that the source end here is V prime, but then here, you're going to add both the incoming and outgoing at the same time right here at the source end. Now, we're going to go ahead and get the currents too. So, if I look at the actual current right here versus time, I don't think Whitworth's book does this. This is going to be I of t. Here's the way I'm going to explain it. learned this in the EMC course, and I made a mistake on this when I started out. So it was on me, I wanna make sure you see this. So, for the current, right there, you really wanna find the voltage across this resistor. Once you have that voltage, you divide it by the resistance and you find the current. Y'all follow? So at the first instance, at t equals 0, we're just gonna get that current. At t equals 0, this is the one I don't think you saw. This would be a time equals 0. I know the voltage here, just as that switch closes, it's basically voltage division at that point. But I have 3 volts here, do you remember that? And I have 4 volts here, so the initial current would be 4 minus 3, or 1 volt divided by 25 ohms. So the current initially would be simply 1 over 25 amps. Help that. All with me on that, class? And the reason is you want the voltage across that resistor. Now that's going to stay that way. 2 nanoseconds, wave goes out, comes back at 4 nanoseconds. That's the round. Now what happens? Well, remember that we had the voltage here at 4 nanoseconds. I forgot what it was. We can, well, what would it be? It would be, it's going to be 3 plus 3/4 minus 3/8, right? So this, the voltage across this side here, it would be, so that's going to be 3 plus 3/4 minus 3/8. So what's that voltage going to be? Because I have to subtract that from 4 to get the voltage across this resistance, which is 25. What is it?
That's 3.375.
This is 3.375, but minus 3/8.
That's 3.75.
Oh, I'm sorry, what did you say?
3.375.
Sorry, 375. And so that would be subtracted from, now remember there's 4 volts over here. So then I'd subtract 4 minus 3.75, and that's
0.625 volts.
what?
0.625.
Yeah, so that means the current right here would go down to 0.625 divided by 25. It's going down. Now, here's the way you think about that. Because it looks like, well, there's more voltage here, there should be more current drawn, but that's not what's happening. This transmission line already had a certain voltage developed on it. Now the change in the voltage is the only thing that's going to be accommodated by this current flowing there. So it will go from that value to this value. Do y'all follow me? And it's going to stay there until what? Now you have to go out and back again, and then you can see what's going to happen. So that would be at 4, 6, 8 nanoseconds, right? 8 nanoseconds. Now what happens? Now you have to take that value, and you have to add minus 330 seconds, and then we didn't even calculate with that, to it, and find the voltage then at across here, and subtract that from 4 volts to see how much voltage is across that resistance. But that's how you would get the current that would be going onto the line, the additional current. And it's going to steadily go down. Well, I say that, it should be less. Now that is for something where, oh my, I'm okay. All right, I'm going to cover, I'll cover the pulse next time, and I'm going to do a few more things, but I wanted to get this out of the way because this is one of these things that is kind of bothering me that people didn't see. I'm just a review for something. I'll see you next time. If you've got questions about the quiz solutions I put up,